So we've introduced the concept of reaction rate and the rate law, which is an equation that tells us quantitatively how concentration affects the rate of a reaction. But we want to see if we can represent this information graphically, visually, as well. So let's just say we take a reaction where reactant A is getting converted into some products. And let's just say that I tell you that this is first order. Again, I'm just making this up. You would not have to figure it out based on this. Well, we've learned already that if we wanted to express the rate, we could write rate is equal to the negative change in concentration of A over the change in time, because we know A is a reactant, so the amount of it is going to decrease over time. We also now have learned that we could express the rate law, rate equals K times the concentration of the reactants. The only reactant is A, and since this reaction is first order overall, the exponent here must just be a 1. So now what we see is we have two expressions to represent the rate for this reaction. Since they both have rate in them, I can set these equations equal to each other. So if I go ahead and make these equal to each other, I now have negative change in concentration of A over change in time is equal to the rate constant K times the concentration of A. Now, why is this important? Well, what we can do from here with a little bit of calculus, so those of you who are taking AP Calc, you can look forward to learning about integration and how to go from this step to the next step. But if we do a little bit of calculus, what we can do is come up with an equation that represents this relationship that we can use graphically. So for example, with a little bit of calculus, we end up with an equation that looks like this. That says, apologies there, that says natural log, that's ln, natural log, of the concentration of A sub T is equal to negative Kt plus the natural log of the concentration of A sub naught. So the way we would say this is the concentration of A sub naught. What this means is the concentration of A initially, at the beginning. So anytime you have this little naught here, this little 0, that means the initial concentration. And this means the concentration of A at some time, whatever that time may be, at 0 seconds, at 5 seconds, at 10 seconds, it doesn't matter. But what this does is this gives us an equation now, if we look at the variables, that can relate the concentration of the reactant at any given time to the concentration that we know initially if we know the rate constant. That's pretty powerful. And we can represent this graphically because if we think about this, this is kind of like a y equals mx plus b. mx plus b. So therefore, if this is linear, essentially natural log of a sub t becomes our y, and t becomes our x. So if we graphed this plot, so we took a lot of data. Let's say we took a ton of data, we took the concentration of A at a bunch of different times. So natural log of the concentration of A at some time plotted against T is going to give us a line with a negative slope. Boom. Where the slope is equal to the negative rate constant. This is just for a first order reaction. So what you need to walk away with, don't worry too much about the derivation, the stuff of the equations here and here. Don't worry about that. What you need to know is that for a first order reaction, if you plot the natural log of the concentration versus time, you'll get a straight line with a negative slope for first order. What if we were dealing with a second order reaction? Okay. A second order reaction let's say if we have A going to the products and this is second order, well, that means the rate law now is going to be rate equals K times the concentration of A. It must be to the power of 2, since this is second order overall, and A is my only reactant. If we go through the same process before, I'm not going to walk through it, but if you do the same process as before, where we set the rate law equal to the rate equation, and we use some calculus, we get an equation, a relationship that looks like 1 over the concentration of A sub T is equal to KT plus 1 over the concentration of A sub naught. So this is the equation for a second order reaction. And the idea is still similar here. This gives us kind of a y equals mx plus b relationship, where now this property, if we take the inverse of the concentration, we put that on the y-axis and we put time on the, time on the x-axis. So time here, 1 over concentration of A sub T. If we plotted this information, we would get a graph with a straight line with the slope that's positive. And slope is equal to K. It would be the rate constant. So again, what you need to know is that for a second order reaction, this is the integrated rate law. If you plot 1 over the concentration on the y-axis and time on the x-axis, you get a line with a positive slope. Third most common one that we would deal with is a 0th order reaction. So let's say the reaction is A produces products, and if this is 0 order, the rate law would be rate equals K times the concentration of A to a power of 0. It's a 0 order. We know anything to the power of 0 is 1, so essentially the rate law would just be equal to K, to the rate constant. Again, if we go through the same process as before, I'm not going to walk through it, you end up with an equation that looks like this. Concentration of A sub T equals negative KT plus concentration of A sub naught. Again, remember, A sub naught means the initial concentration. A sub T means the concentration at any given time. Again, this gives us the form of y equals mx plus b, where now on my y-axis, I would put concentration of A, and on my x-axis, I would put T. So that if I plotted this graphically, I take the concentration of A, whatever A is, the reactant, and plot it against time, what I'm going to get is a negative slope, so a line pointing down, where the slope equals negative K. Okay? So these are the 3 main orders of reaction that we need to know how to use and recognize. These are all called the integrated rate laws, these 3 equations, because they're determined from integration, which is something that's used in calculus. Now, why is this helpful? Well, in summary, we have 3 different orders: 0th order, 1st order, and 2nd order reactions. Rate laws, if there's just one reactant, would look like this. Remember, this could also be, K times the concentration of A times the concentration of B. That would give you 2nd order overall, because this would be 1 and 1. But what you need to know is these equations help us figure out what order the reaction is by making 3 different graphs. So again, let's say you're doing an experiment. We're going to actually do this in class. And you measure the concentration of, let's say we're doing some reaction, A to products. And what we do is we set up this reaction and we measure the concentration of A at 0 seconds, and then we measure it at 10 seconds, at 20 seconds, at 30 seconds. We measure how the concentration of A is changing over time. If we take that information and we graph it, okay, and we graph it in 3 ways. We graph it where we just do the concentration of A, versus time. We do the concentration, the natural log of the concentration of A versus time. And we do 1 over the concentration of A versus time. Only one of these graphs would give us a straight line. Whatever graphs gives us a straight line, that tells us what order the reaction is with respect to that compound, which is pretty cool. So let's say you collected all this data, and you got a curve here, you got a curve here, and then you got a straight line when you made this plot. That would tell you for sure that this reaction must be second order. And what we'll do is we'll get a lot of practice in class with looking at these graphs and figuring out how to determine the order. Then we'll actually do this as a lab, and we'll have a solid understanding of the rate law in practice.